Hello friends. So this in today we are going to discuss few of the 2020 or 2020 mains questions. In the first one, a 750 Hz 20 volt RMS source is connected to a resistance of 100 ohm and inductance of 0.1803 Henry and a capacitance of 10 microfarad all in series combination. The time in which the resistance having the heat capacity of 2 joules per degree centigrade will get heated by a 10 degree centigrade is close to assuming no loss of heat to the surrounding. In this case, we are supposed to find out that the time by which the temperature of the resistance is raised by 10 degree centigrade. So means the value of delta T is about 10 degree centigrade. So this is basically a series RLC circuit. So let us calculate few of the parameters that will be used later on. So we have a series RLC circuit. First of all, let us try to find out the angular frequency. Which is omega, and that will be equal to 2 pi f. F is given to us as 750. So this is 2 pi multiplied by 750, and this comes close to 4712 radian per second. Now we can find out easily the inductive reactance as well as the capacitive reactance. So first is our inductive reactance. XL will be equal to omega L, and omega is our 4712, and inductance is given as 0.1803. So we get our XL is approximately equal to 849.64 ohms. Similarly, we find out the capacitive reactance. That is our XC, which will be equal to 1 omega C. Omega we found out is our 4712. Capacitance is given to us as 10 microfarad. We can say our XC will be approximately equal to 21.22 ohms. Now we can find out the impedance. That is our Z will be equal to R square plus XL minus XC whole square and its square root, and we simply substitute values. It comes approximately equal to 834.67 ohm. Now we can find out the RMS current that will be flowing in the series circuit. We can say RMS current that is our IRMS will be equal to VRMS divided by Z. VRMS is given as 20, and we just found out our Z, that is 834.62. So we got our IRMS will be approximately equal to 23.96 milliamperes. So as it is series RLC circuit. So this RMS current will be flowing through all the components, that is inductor, capacitor as well as resistor. We are only interested in resistor. So you can say power dissipated in resistance. If that is given as P, which will be equal to I RMS square multiplied by R. We substitute the values. We get P is equal to 23.96 whole square and multiply by R, that is given as 100. So we get our P is approximately equal to 0.0574 watts. This is the average power dissipated in the resistance. And we are interested in time, which raise the temperature by 10 degrees centigrade. So we can say the heat energy required let us call that as Q. Then this Q will be equal to S multiplied by delta T. And S is given to us, that is our 2. Delta T we know is our 10. So this comes as 20 joules. So we can now easily find out the time to heat the resistance. Time to heat the resistor. So in this case we are going to use the definition of the power. So we can say our power is equal to heat energy required divided by time. So we can say time is equal to Q upon P. Q we just found out is our 20 and power is our 0.0574, and this will be approximately equal to 348 seconds. You can see our time required to raise the temperature of the resistor by 10 degrees centigrade will be 348 seconds. And the option number D is the correct option. Option D is correct. Now let's move to the next question. And in this case we are given that we have an elliptical loop having resistance R of a semi-major axis A and semi-minor axis B is placed in the magnetic field as shown in the figure. If the loop is rotated about the x-axis with the angular frequency omega, then the average power loss in the loop due to joules heating is given as. So we have a figure, and this we have a elliptical loop which is having a major axis A, minor axis B, and we have a magnetic field which is in Z direction, and the major axis, XY plane. Okay. So if we say A is the area of the ellipse, area of ellipse A, then it will be equal to pi multiplied by AB, product of semi-major and minor axis multiplied by pi, and magnetic field that is our B is along z axis, so we can write this as B with a k unit vector, and it says that the loop rotates about x axis. Yeah, you can say that loop rotates about x axis, and it is given with the angular frequency omega with angular frequency that is given as omega. And we can assume that at time t is equal to 0, the loop is in the plane xy plane. So we can say that at time t is equal to 0, assume the loop's plane is xy plane. Therefore, from here we can write that our area vector will be equal to pi a b, and we have this as a k unit vector. And obviously when it is going to rotate, the normal of the normal to the plane, that is our area vector, changes its direction. You can say it rotates such that the normal to the plane, which is nothing but our area vector, the normal to the plane area vector changes direction. Because initially it is along the k unit vector, that is our z axis. So if we assume, or rather we can say it is given, that the loop rotates about x axis, a loop rotates about x axis, and if we assume that theta is the angle between the magnetic field and the area vector is also going to vary with time, because our magnetic field will be, you can say, in the z direction, always in z direction, whereas as the loop is going to rotate, the area vector is also going to change its direction. Therefore, we can say from here that the angle theta between magnetic field and area vector varies with time. So the angular position theta it can be written as omega multiplied by t. And we can also assume that initially, like we said, that at time t is equal to 0, the loop is placed on an xy plane. Okay, and the figure it is also given that it is in the xy plane. So here we can just write it assuming theta is equal to 0 at t is equal to 0. So we are mainly interested in now you can say the area vector, its z component, because our magnetic field is in z direction. So we can say area vectors z component. So we can just you can say make a projection of area into the xy plane. So you can say that projection of area onto yz plane which is nothing but perpendicular to perpendicular to x-axis, perpendicular to x-axis changes because it is going to rotate, but the effective area perpendicular to B, that is our along the z-axis. So we can say effective area perpendicular to our magnetic field which is along z-axis. We can write this as A of z will be equal to A cos of theta, and we substitute the value of A as well theta. We can write this as pi AB cos of omega t. So from here we can easily say when theta is equal to 0, when theta is equal to 0, plane of the loop is xy and is perpendicular to the magnetic field, and when theta is equal to 90, theta is equal to 90 degree, the plane is you can say xz, the plane is xz parallel to magnetic field, which basically means that in this case we are going to have zero flux. So therefore we can write the equation of the flux also. We have our magnetic flux, that is our phi will be equal to B A. We substitute the value, we get B multiplied by z vector z component of A, and we can write our flux phi will be equal to B pi AB cos of omega t, and we can just simplify it, or rather we can say arrange. This will be pi AB B cos of omega t. Now we have to find out the induced EMF. Induced EMF, it is nothing but negative of rate of change of magnetic flux. So induced EMF is equal to minus d phi by dt. and we substitute the values. We can easily do its derivative. We get this as minus d upon dt. This is our pi a b magnetic field cos of omega t, and this gives us that our magnitude, mainly interested in magnitude, so we can say this as pi a b capital B omega, and we have here sine of omega t, and we can find out the peak EMF. Peak EMF, let us call that E peak, which will be equal to, when sine of omega t will be equal to 1, and we can write this as pi a b multiply omega, and this is under the condition that sine of omega t is equal to 1. Now finally, we are going to find out the current in the loop, and then we are going to find out the average power. So we have current in the loop, which is our I, and that will be equal to EMF divided by resistance R. We already found out our EMF, so we can find out our current. Let's make it time dependent, because our EMF is also our time dependent. We can say E of t, and its magnitude will be equal to pi AB magnetic field omega R, and here we have sine of omega t, and we can also find out the peak current. We can call this as I peak, which will be equal to pi AB magnetic field omega divided by R. Now we can find out the power loss. So instantaneous power loss, which will be equal to over P, or let me write it here, P is equal to our I square R, and we can also make it a time dependent function. So this becomes P I of t square multiplied by R, and we substitute the value of current, which we just found out, and that is equal to pi AB magnetic field omega divided by R, and we have sine of omega t whole square multiplied by R. So we get instantaneous power is equal to pi AB and our magnetic field omega whole square divided by R, and here comes as sine square omega t. Now we can find out our average power loss. Average power loss, because this in the equation we can see that our power is basically time dependent function. So it means we need to do a time average over one complete cycle. So you can say, since P of t varies with time, we need the time average over one complete cycle. And if its time period is given as capital T, then capital T will be equal to 2 pi upon omega. So we can say our P average will be equal to 1 upon T integration 0 to T P of T and dt. So if we substitute the value, P average is equal to 1 upon T 0 to T, and we already know our P of T, that is our pi AB magnetic field whole square divided by R, and here we have sine square omega t and dt. So only time dependent is sine square omega t. So we can just move rest of the things out of the integration. So we can say this as P average will be equal to pi AB magnetic field omega, and this have whole square R, and this comes as 1 upon T integration 0 to T, and we have sine square omega T multiplied by dt. And we are only interested in the integration of this trigonometric identity, and which is quite simple. So we can just write the formula here. This comes as equal to pi a b b omega whole square R multiplied by 1 upon T and multiply by its integration will be equal to, its integration will be equal to, inclusive of this 1 by T, this will be coming as 1 by 2. So therefore you can say the average power that is a P average is equal to pi square a square b square magnetic field square omega square divided by 2r. And the option that are present or given to us, option number A is the correct one. Option A is correct. So these were the question for our 2000 main. So this completes the questions. Thank you.